All right, everybody, this is section 6.8, which is talking about the trigonometric inverses and their graphs. So we've already talked about all the other trig functions and their graphs. So every one of those trig functions has an inverse. So we've used those before when we were solving for angle measurements, especially like in the SOHCAHTOA triangle sort of things. But we've definitely had the idea of inverse before. So I just want to start today with a warm-up question just to make sure you remember how to find an inverse, what that is all about, and then what does that look like for the ones that are trig functions. So if you think back way back to earlier in the year, how do you find an inverse? Well, you take the domain and the range values and you switch them. So we switch the domain and the range. So what that means in our lingo usually is you're switching the x and the y. So the inverse equation is when the domain and the range are inverted. And remember, their graphs, they're always reflected over the line y equals x then. So the symmetry that those graphs would have, the original function and the inverse, are always symmetric with respect to the line y equals x. So let's try it just for a regular old linear function like what we are used to seeing. So if you were going to graph that line, it'd have a slope of 2, y-intercept of 5. If you're going to find the inverse, you'd switch the x and the y. So we'd have x equals 2y plus 5, and technically that's the inverse equation. But just for convenience sake, what we would normally do at that point then is just solve for y. So we would be able to see what it looks like and be able to graph it a little bit easier. So if you solve this equation for y, we'd subtract the 5. Make sure you always do opposite operations. Divide by 2. So some people might leave that equation as y equals x minus 5 over 2. For me personally, though, I think it'd be a lot easier to see the slope in the y-intercept. So I would say 1/2 x minus 5/2. So that would be another linear equation. So the inverse notation that we used before, we did this. We'd say f inverse of x then would be 1/2 x minus 5/2. So it's another linear equation with a slope of 1/2 and a y-intercept at negative 5/2. So this inverse is a function. Now, that's not necessarily the case for every time we take an equation and we find its inverse. If you do a parabola and you find its inverse, the inverse of a parabola is the square root, which technically, plus or minus, is this, which would not be a function, wouldn't pass the vertical line test. So it's not a certainty for us that if we take the inverse, that we're necessarily going to get a function. We're going to get another relation, but not necessarily a function. All right, so let's take a look at what this looks like for cosine. So it would be the same process to work through for any other trig function. So this would be the same for sine or tangent, whatever. So I'm just picking cosine to do this for. And again, you could do it the same thing for any of the other functions. So we're going to go ahead and switch the x and the y. So we're going to switch those. And then again, we're going to need to solve for y for convenience sake. And especially in this situation where you're switching the domain and the range around, it's helpful sometimes to look at that. So if we switch the x and the y, solve for y, we have to get rid of the cosine part here. So we need to undo that. So to undo cosine, we use inverse cosine on each side. So I'm going to take the inverse cosine of each side of that equation. So it's an actual operation. It's like taking square root on both sides. You're doing that inverse operation. It's not multiplying by cosine. Multiplication is its own operation. This is actually doing the inverse cosine on both sides. So on the right-hand side, if we take the inverse cosine of the cosine, those are opposite operations. They undo each other. We're left with y, and then we have inverse cosine of x left on the other side. And you can do this same process for any of those trig functions. So some people write it like that. Remember, arc cosine means the same thing. That is another word that we have for inverse. So we've used that before, this prefix arc. So either one of those would be inverse equations for cosine. So on your calculator, we see the -1 notation. It's above the cosine key. Arc is a little older term, but it's the same function, so it means the same thing. All right, so let's write this out, what this looks like then for all of the functions. So I'm going to go through sine, cosine, and tangent and talk about what the original looks like and then compare that to what the inverse does. So we'll kind of fill in the information that we know. So let's start with sine. The original equation relationship is y equals sine of x. So that's our original function. The ordered pairs then, when we write our ordered pairs, so x, y, means we have x and then we have sine of x. Our y value is whatever sine of x is. So I like to think of it this way. You're putting in an angle and your answer is the ratio. So when we think about domain and range, our x values are the angle measurements, our y values or outputs are the angles. Okay, what does one complete cycle look like? So we're just going to show really rough sketch here. So up to 2 pi, pi over 2, 3 pi over 2. If you need to put all the labels in there, 1 and -1. Okay, so the sine graph, original graph, starts in the middle, max, middle, min, middle. So it looks something like this. You guys know what that does. The domain, because of those arrows, all real numbers. So -infinity to infinity, or if you prefer, you can say all real numbers. And then the range is -1 to 1. So the outputs, those values are -1 to 1. Okay, so what happens when you do the inverse? So we would take the inverse sign on both sides. So the equation when we solve would be the inverse sine of x, or if you prefer, the arc sine of x. What does that mean when you find inverse? The ordered pairs switch. That would be y comma x, which means sine of x is first, and then x. In other words, your ordered pairs now are ratio comma angle. That means you're given a ratio and your answer is at what angle does that occur. So when you're plugging in a number into an inverse, I'm giving you the ratio, you're going to tell me what the angle is. So it's the same ordered pairs, they're just inverses of one another. They're just switched. Okay, let's take a look at what that would be then for your graph. And this is kind of crazy, but now your domain is going to go from -1 to 1, and your range is going to go from 0 to 2 pi. So the x and y axis have to switch. So the labels are going to look the same. They're just on the opposite axis if we change those. Now sine, just do your ordered pairs. Take every single one of these points on your original graph and switch them. So 0, 0 would stay the same. Okay, we had the point pi over 2, 1. So now we're going to, oops, why did I label that a -1? That's crazy. That should be +1. Sorry about that. So for this next point, pi over 2, 1 would be 1 pi over 2. And then we have pi 0, so 0 pi. 3 pi over 2, -1, so -1, 3 pi over 2. And then 0, 2 pi would be the inverse for 2 pi 0. So your graph actually is a curve again, but it's going up and down the y-axis now instead of across on the x-axis. So it's a very different graph when you look at that picture. So domain and range switch. That means our domain now is -1 to 1. Oops, I was doing green before. I'll just keep my color coding here. So -1 to 1. And then the range, the output, is the one now that goes infinitely large and small. So when you look at the inverse, this is not a function. So when I think about the picture of that and I do a vertical line test, the inverse of sine is not a function. So I'm going to have to deal with that when we look at how the graphing calculator handles that too. We'll talk a little bit more about that. So that's what the inverse graph looks like. It's going to go up and down the y-axis instead. Okay, so we're going to do the same thing for cosine now to get the same idea out. So the original function is y equals cosine of x. So that means your ordered pairs, the x comma y. That means it's x cosine of x. So you put in an angle, then you get a ratio out. So the original function, angle, then ratio. All right, let's do your quick graph here. So we have our sketch. So we go out to 2 pi and 1, -1. So now cosine starts at its maximum, middle, min, middle, max. So it looks like this. The domain, again, all real numbers. You can use any angle measurement you want, so -infinity to infinity, or if you prefer, all reals, and the range -1 to 1. Sine and cosine are so similar, so much in common. All right, now let's talk about the inverse then. So inverse cosine, we can write with the inverse notation, or you can write with the prefix arc. Remember we talked about that before, arc cosine. That means your ordered pairs for the inverse were y comma x for what we were thinking about before. So that means we'd have our cosine value first, and then the angle measurement. So that means it's a ratio, comma, an angle. So I'm putting in a ratio value. So I'd be putting in the 1/2, the square root of 3 over 2, the 0, and my answer then would be at what angle does that occur. So my x and y axis are actually flip-flopping. So again, just like with sine, my angles will be on the y-axis, and my ratios are on the x. All right, so now cosine. Again, we're going to take every point, every ordered pair on the original graph, and just interchange or switch the x and the y. So 0, 1 would be 1, 0. Pi over 2, 0 would be 0 pi over 2. Pi negative 1 would be negative 1 pi. 3 pi over 2, 0 would be 0, 3 pi over 2. And then 2 pi 1 would be 1, 2 pi. So when you see this picture, this curve, smooth continuous curve, it's going to continue in both directions. It's not going to be a function again, just like sine wasn't either, because we have infinitely many outputs. So just like in sine, when we do the inverse, the domain becomes negative 1 to 1, and the range now is infinite, from negative infinity to infinity. So when we look at those pictures, it's definitely not going to be a function. All right, let's take a look at the last one, the parent graphs. We'll talk about tangent. So our regular graph for tangent, y equals tangent of x. When we think about the ordered pairs, x, y, we would have input would be the angle measurement, the output would be the ratio. So we put in an angle. Our answer would be a ratio. I'm going to graph one complete period for this one. So going back, I know we haven't done these graphs quite as much, but one complete graph is only pi long for tangent, and the easiest one to graph goes from negative pi over 2 to positive pi over 2. So we still do 4 tick marks, just like we did for sine and cosine. I just think it's easier to think of it on each side so we don't have like pieces of that graph. It's undefined at negative pi over 2. So I'm just going to put in a vertical asymptote there where those are undefined, and positive pi over 2. Tangent at 0 is 0. And tangent at pi over 4 is 1. And tangent at negative pi over 4 is negative 1. So this graph does something like this and approaches those asymptotes. Now I'm going to show that this graph continues. I'm going to put arrows just to show that that graph keeps going. So it's not just one of these. This curve that I just drew would repeat infinitely many times. So in the original graph, it's not restricted. It's going to keep going. All right, so what does that mean? Well, the range, if you look at the top and the bottom of the graph, we have arrows. Just like we talked about before, that means the range is everything. But for domain, a little bit more complicated. It's all real numbers, but x can't be any multiple of pi over 2. So pi over 2 plus pi k. The period is pi. So every pi, starting at pi over 2, we're going to have an undefined place. So basically any multiple of pi over 2 is bad business for tangent. Okay, so what would inverse tangent look like? So the equation would be inverse tangent or arctangent, which means our new ordered pair that we have to flip-flop. That means our tangent value comes first, then the angle. In other words, we would have ratio, comma, angle. Trying to fit this all in there. That doesn't look really nice. So ratio, comma, angle. So that means, once again, kind of goofy, but when we make our xy axis now, angles have to go on the vertical scale. So we'd be going from negative pi over 2 to positive pi over 2. And on the x-axis from negative 1 to 1. So actually the values are going to flip-flop. All right, so what happens then? We take every point and we flip. So let's do the ordered pairs. So 0, 0 is still going to be 0, 0. We had pi over 4, 1, so it's going to be 1 pi over 4. Negative pi over 4, negative 1. So we would have negative 1, negative pi over 4. The undefined places were vertical lines. So if we switch the domain and the range, what was vertical is going to become horizontal. So now we have a horizontal asymptote on our graph at pi over 2 and negative pi over 2. And then the curve looks something like this. Now, technically, I'm going to show the arrows. It's going to continue infinitely in both directions. So you're going to have these stacked one on top of each other infinitely in both directions. So this one is not going to be a function either, because you're going to have all of those different curves stacked on top of one another. All right, so let's switch our domain and range. That means our range, look at where the arrows are going left and right, is going to become the domain. So we can use anything we want for the domain. The range, the outputs, the y's are where we're going to have trouble. It would be all real numbers, but y, remember it's the output, can't be Same thing, pi over 2 plus pi k. Any multiple of pi over 2 is going to be bad business for our values that we're going to be looking at. Okay, so let's talk about this idea of what you can and can't use then. We have an idea, something called principal values. The issue that we're going to run into, oops, I skipped a slide here. The issue that we're going to run into is that the inverses of the trig functions are not functions themselves. So the inverses are not functions because they don't pass the vertical line test. So that means every time we do an inverse, we'd have infinitely many answers. So we don't have to deal with that, kind of like we restricted before, so we only looked at the unit circle. We're going to do the same thing. We're going to restrict the domains of the original functions, so the inverses will be functions. Why does that help? Well, if you restrict the domain of the original, that means the inverse's range will be restricted, right? And it's the output that we're concerned about, right? Because that's where we don't want to have more than one output. For every x, there has to be exactly one y. So if we can restrict the domain of the original function, when you switch the domain and the range, then the output or the range will be restricted, and then they will be functions. So those restricted values, those are called principal values. This is what your calculator is programmed to do. When you do an inverse sine or an inverse cosine, think back to when we were solving triangles. It didn't give you a whole bunch of answers. It gave you one answer. So we know that our calculator is already programmed to do it. And this is not the only thing that's programmed that way. What about square roots? Technically, when you take the square root of 9, it should be plus 3 or minus 3, but your calculator, try it, only says 3. That's the principal root. So they use that principal meaning most important. If you've ever seen like a roster of an orchestra, they talk about the principal player, meaning like the section leader, the most important player. So principal meaning the most important. So we use capital letters, though, to differentiate when we're talking restricted versus unrestricted. So people know, is this the one that has the domain of everything, or is this the one that it's restricted? So you'll see capital letters when they are meant to be principal values. All right, so let's fill in the chart here so you can see what we're talking about. So capital letter sine, that means the restricted domain for sines. Remember, we restrict the original function's domain, so the range of the inverse will be restricted. All right, so let's talk about what the restrictions are. So for sine, if we go from negative pi over 2 to pi over 2, inclusive, so ends, that will give us all the values that we need to make all the values of sine. Let's think about why that is. Negative pi over 2 is down here. Positive pi over 2 is up here. So if I restrict from negative pi over 2 to pi over 2, I'd be getting quadrant 1 and quadrant 4. Sine is positive in quadrant 1. It's negative in quadrant 4. That will give me every special value exactly one time. If I kept going into either quadrants 2 or 3, I would start repeating values that I already have, so I don't need them. So I can just go from negative pi over 2 to pi over 2. Seems kind of goofy to do that, but those are the only two consecutive, like right next to each other, quadrants that are easy for someone to use for sine. So that means my range, though, is still negative 1 to 1. I still have all the values for the ratios. So that means the inverse arc sine, those just flip-flop. So that means the range will be negative 1 to 1. Will become the domain. Didn't have any issues with that. That's what those outputs were. But now here's the cool thing. The range for the inverse is only going to go from negative pi over 2 to positive pi over 2, and that will be a function because we're not going to repeat values. You'll see that in a second when we do the graphs. Okay, well, let's restrict cosine the same way. Cosine, the restriction's a little bit more user-friendly for people to think about. They restrict cosine to be 0 to pi. Why does that work? Well, 0's here, pi's here. That means we'd be talking about these two, quadrant 1 and quadrant 2. Well, cosine is positive in quadrant 1. It's negative in quadrant 2. We'll get all the values for cosine happening in those two consecutive quadrants. If we kept going in either one of those, we get more negatives or more positives that we already had. We don't need them. That gives us everything one time. And again, once again, this is still negative 1 to 1 for the range. Okay, so what does that mean for our inverse? Arc, and remember the other way to write that is inverse cosine with that capital letter. Same thing here, inverse sine with the capital letter for S, so you can write it either way. That means our Domain, well, that's going to be what the range was. No problem there, but here's the cool part. 0 to pi. I'm only going to get the answers once. It will be a function. Okay, capital letter tangent. What's my restriction for tangent? It's exactly the same as sine, those two consecutive quadrants. But notice the difference. They're parentheses. So parentheses mean not included, because technically tangent isn't defined at negative pi over 2 or pi over 2, so you really can't have values there. But it's the same restriction. It's quadrants 1 and 4. And again, those are the only two consecutive quadrants where tangent would reach all of its values. Tangent is positive in quadrant 1, negative in quadrant 4. So those are two quadrants right next to each other where we get all the values for tangent. If I continue on again, I'm going to repeat values that I don't need. All right, so that means our output values here for tangent then, everything, and that's fine. Negative infinity to infinity, those are where the arrows are going for tangent. But when I do the inverse now, and remember that could also be written like this, inverse tangent with a capital letter T, same thing. My input is anything. Those curves will be going side to side. But here's the cool part now again. I'm only going to go negative pi over 2 to pi over 2. That'll be the restriction I need to only have a function for that output. So what we're going to do here is we're going to go through and make graphs of each of these so you can see what that looks like with those restrictions. So we'll see what that picture looks like. So when you graph regular old sine, capital sine, it goes from negative pi over 2 to pi over 2. And it goes from negative 1 to 1. So this is like thinking about graphing the regular graph for sine between negative pi over 2 and pi over 2. Well, sine of 0 is 0. Sine of pi over 2 is 1, and sine at negative pi over 2, that would be negative 90, would be negative 1. So your graph, that little piece of sine, would be just this. Notice, really important, no arrows on the end because it doesn't continue. The limitation for domain is negative pi over 2 to pi over 2. So this is really important. Make sure you know that's limited. Okay, so for inverse then, the domain and the range switch. So that means we're going to have our pi over 2 to negative pi over 2 on the y-axis, and negative 1 to 1 on the x-axis. Take every one of these ordered pairs and switch them. Well, 0, 0 is still going to be 0, 0. Pi over 2, 1 is going to be 1 pi over 2. And then negative pi over 2, negative 1 would be negative 1, negative pi over 2. Okay, the points are in exactly the same spot. People get kind of messed up on this. The curvature changes, though, because remember, these are going to be reflections over the line. And I'm going to put it in just lightly here, y equals x. If you reflect over the line y equals x, the 3 points are going to stay in the same spot, but the curvature is going to change. So where that blue curved away from that red dotted line, this one is going to look something like this. It's going to curve in like that, and then away from the dotted line there. So the curvature is different. These are reflected over y equals x. It is a different graph because remember, this one is curving up and down on the y-axis, but notice it stops, right? So there are no arrows. If you looked at this red graph, it would pass the vertical line test. It is a function. So I'm going to go back and think about those original graphs here for sine. I'm going to go way back to that original one. So if you think about what we did for sine here before, what you're seeing of the sine graph is now this. That little piece, and it's not repeating, it's not continuing up and down, so it is a function. So we made that restriction. So again, that's how your calculator is programmed. All right, let's do cosine, do the same thing. The restriction for cosine, remember, for your domain is 0 to pi. So that means I'm just going to go up to pi on the x-axis. And I think we'll spread that out a little bit so it's a little bit easier to graph here. So pi over 2, and then 1 to negative 1. So cosine starts at its maximum, goes to the middle, and then down to the min. So it looks like this. And again, no arrows, it doesn't continue. That means on the inverse, we're going to go 0 to pi on the y-axis now. And the x-axis is going to go negative 1 to 1. So when we do our flip here, we had 0, 1, so now it's going to be 1, 0. And then pi over 2, 0, so 0 pi over 2. And pi negative 1 pi. And just be careful for the curvature now again. The way that this has to curve to go up and down the x-axis or the y-axis would look like that. And again, look, this is a function. It's going to pass that vertical line test. It's not going to touch more than one point. It's not continuing past. So if you go back to your original cosine graph that we made, so going back to this picture, all you're seeing for the cosine part is this first chunk, which is not going to be repeated then. It's only having every value one time, which is what we were looking for. Okay, tangent actually looks a lot the same as the original. When you just graph a single one of them, the restriction for tangent for domain, remember, is the same as what it is for sine, just not including the endpoints because technically they are not included in the domain of the function. So negative pi over 2 to pi over 2. It's kind of helpful to have our quarters in here as well. So pi over 4, negative pi over 4, and 1 to negative 1. All right, so what does tangent do? It's undefined at negative pi over 2 and pi over 2. And then 0, 0. Pi over 4, it's 1. Negative pi over 4, it's negative 1. And we get this curve. Now, this may look exactly like the one we did before. However, the difference is it doesn't continue to the left and to the right. That does not happen. It literally stops at those two undefined places. There's only one cycle of the graph, and that's it. Because then when we do the inverse, so we go pi over 2 to negative pi over 2, negative 1 to 1. So the x and y axes switch, remember, so the angles are on the y now. Negative pi over 4. So now our horizontals are the undefines. And switch all these points. 0, 0, still 0, 0. We'd have, instead of pi over 4, 1, 1 pi over 4. And then instead of negative pi over 4, negative 1, negative 1, negative pi over 4. And we get this curve. But now it's a function because it doesn't repeat. It's just this single curve. There's nothing stacked above or below it. So that would be the value of that function. Okay, so to finish up with what we're going to do here, I want to do a few examples just to go through how are we going to interpret and use these values in questions. And so we know what the graphs look like. Have to pay close attention to what the capital letters mean. The nice thing about this is it means I'm only going to have one value because it's a capital letter. So we only have every single value that we get just one time. So if you see arc, could be written like this as well. So I just want to show you the two different ways. What they're asking you for, what this question means, is they're giving you a ratio. So they're telling you a ratio. They want you to answer with the angle measurement that makes that true. So if you're answering an inverse question, you're answering the question, what angle does this happen at? So it's always what angle. So when is cosine square root of 3 over 2 in that restricted domain? Well, cosine is square root of 3 over 2 at 30 degrees, or you can say pi over 6. It doesn't matter. It can be in degrees or radians. But here's the cool thing. It's just that one, because your restriction for cosine, remember, is 0 to pi. Or, if you'd rather, that's the same thing as 0 to 180. You only have to give that one value. Okay, what if you see parentheses like this? Well, start on the inside and work your way out, just like normal order of operations. This is a special value. This is regular sine, though, so it's sine of an angle. So the first thing I'm going to figure out is what is sine of pi over 2. So you're given an angle, sine of an angle. That means your answer should be a ratio. So what ratio do you get? What is sine of pi over 2 or sine of 90? Well, it's 1. Okay, so that means I need to take the inverse cosine of 1. So what does that mean when they say inverse cosine? That means, okay, I'm giving you this ratio. I want you to tell me for what angle does that happen at. So what angle measurement would cosine be 1? That would be 0. 0 radians or 0 degrees, which fits right into our restriction for cosine. It has to be between 0 and pi. But the cool thing is, again, I only have to worry about one of those answers. Okay, a couple more. Let's start on the inside and work our way out. So we're going to do this first. Inside the parentheses, inverse cosine of 1, asking the question, for what angle is cosine 1? So this is the ratio. You want the angle measurement. Well, what angle is cosine 1? First time it happens in our restricted domain is at 0 degrees or 0 radians. So however you want to say that. Okay, let's try this. Inverse sine of a half. That's asking the question for what angle, so they're giving you the ratio of a half. Oops, R, ratio. What angle measurement would that be? When is sine a half? Well, the first time it happens is at 30 degrees or pi over 6, whichever way you want to think of that, degrees or radians. So that's the only one we need though, because that's the one that's in our restriction. Sine is restricted to be from negative pi over 2 to pi over 2, or negative 90 to 90. So if you'd rather think of it that way, that's fine too, if you want to think of it in degrees. So we only need that one answer. So what did that give us then? Well, inverse cosine was 0. Inverse sine was 30. You can do it in degrees or radians. Just do the arithmetic on the inside. So we need sine of 0 plus 30. So we need sine of 30 degrees. What is the sine of 30 degrees? 1/2. So we can use order of operations to help us kind of sort through things. Okay, let's finish up the last couple here. I know this is kind of a long one. It's a lot of information. Start on the inside. Inverse sine of 2. That's giving you a ratio of 2 and asking you for what angle does that start at. So what angle would that be? Well, can sine ever be 2? Think of your outputs. Only goes between -1 and 1. That is physically impossible. If you try starting or typing that in on your calculator, it'll say error domain. There's no way that it's going to be able to do that. It's not going to be able to solve for either of those values. So some of these are not possible. You can't just plug in any number you want. Okay, so our last couple here. Inverse tangent of -1. So when is tangent -1? So it's asking the question for what angle would that happen. So this is the ratio, and you want to figure out the angle measurement that would be. Okay, well remember the restriction for tangent. It's from negative pi over 2 to pi over 2, or if it's easier for you to think of it, negative 90 to 90. Okay, so what angle measurement, what reference angle is tangent equal to 1? Well, that's at 45 degrees, right? But if we want -1, that has to be at a quadrant where tangent is negative. Now let's think about this. If it's positive, that means it's in quadrant 1. That would be the 45-degree angle above. Since this is negative 90 to 90, or negative pi over 2 to pi over 2, that means the one that they want has to be a quadrant 4 angle. But you got to be careful how you label it. We would call that negative 45 degrees then. We went down instead of up to get that -1 value. So you could say negative pi over 4 or negative 45 degrees. What you couldn't say is 315 or 225 or any of those other numbers, because these are not between negative 90 and 90 or negative pi over 2 to pi over 2. So you just got to be careful how you label it. I know they're coterminal, but you have to label it in negative 90 to 90. Try it on your calculator. Put your calculator in degree mode and type in inverse tangent of -1. It will tell you negative 45. It will not say 315. We want to be consistent with how we're answering that. So let's try one more of those. So here's the ratio that we're looking at. So inverse sine -1/2. We want to figure out what angle measurement would that be. That's what inverse means, at what angle. So it's the same ordered pairs, but we're just trying to figure out when that is. So our restriction is negative pi over 2 to pi over 2, which is the same thing as negative 90 to 90. And we're going to try to figure out when is sine -1/2. Let's think reference angle first. When is sine just positive 1/2? When does that happen? Well, that's 30 degrees. So that would be in quadrant 1. So if this was a positive 1/2, you would just be saying 30 degrees or pi over 6. Either one, it means the same thing. How do I get a negative 1/2? Well, if our restriction is negative pi over 2 to pi over 2, or negative 90 to 90, that means I'm going to have that same reference angle, but down in quadrant 4. I need to go down that distance. So that means the reference angle would be negative 30 or negative pi over 6. So my answer here, what I'm looking for, is negative pi over 6 or negative 30, depending on whether you want to be in degrees or radians. You would not be able to label it 330 or any of those. I know they're coterminal, but they're not between negative 90 and 90. So you really have to be careful on the labeling. It's coterminal, but it has to be between negative 90 and 90. So be careful. Try that on your calculator. Make sure you're in degree mode so you can see it better. Do inverse sine of -1/2. It will say negative 30. So this idea of inverses, switching the domain and range, we're looking for values where we're answering the question, if this is the ratio, at what angle does that happen? We restrict them so we can have functions, so we don't have infinitely many answers.